So what's going on here? Oh, I think what happens here is that a sort of common sense view of how perception... So there's a kind of common sense view that says that perception is about this kind of passive imprinting of the world on the sense organs. You know, your sense organs are inside, the world is outside, and the world comes in through the transducers. So this is a picture from Descartes, did lots of lovely work in these sorts of areas. Same sort of picture has been around in neuroscience. This is a quote from Egner in 2010, not a fan of this story, but putting it forward just as a contrast. He says, on traditional accounts, the visual system was seen as a passive analyzer of bottom-up sensory information. So this is a kind of view of the brain as a sort of passive, highly stimulus-driven organ. It's kind of sitting there waiting for stuff to come in from the external world. This is a kind of view that Pat Churchland, for example, in a paper with Sanofsky and somebody else, Ramachandran, some years ago in 1994, I think, a critique of pure vision, did a very, very fantastic job of casting doubt from all kinds of angles on this sort of hierarchical feed-forward story. So what's being cast doubt upon here is what you could think of as a kind of cognitive couch potato view of the brain. The brain just sits there waiting for stimulation to come in from the external world. When it comes in, it proceeds to process it step by step, layer of the hierarchy by layer of the hierarchy. So I think that what predictive coding offers is a kind of opposite, the extreme, the most extreme opposite possible to the cognitive couch potato view of the brain.
Ned Flanders.
Pardon?
Ned Flanders.
Ned Flanders.
Indeed. Whatever that is, but you tell me later.
This is Simpsons.
Oh, Simpsons, right, yes, yes. So I think it's the opposite of that. Yeah. Okay. So what's going on in, what would the opposite of that look like? I think the opposite is you've got a brain which is constantly active, and the job of that constantly active organ inside your head is to predict the incoming sensory signal. And it's to predict that signal at as many scales of space and time as it can manage to. And it's doing that job at these many scales of space and time that the basic hierarchical elements of the organization are serving. So when Pat and Sanofsky cast doubt on the feed-forward hierarchical model of processing, I think it would be a mistake to throw away the hierarchical bit of it just because you're throwing away the feed-forward bit. What we've now got, I think, are very interesting hierarchical downwards-looking models. So we can talk about how strict the hierarchy has to be if you want to. Okay. So when things work in this kind of way, it seems to me that we get an account not only of how we perceive the world, and we'll look a bit more at what that account looks like in the next 5 minutes, but we also get an account of why it is that when we perceive the world we understand it, and we also get an account of why it is that when we perceive the world we're in a position to imagine it, which is actually quite close to being in a position to reason about it offline, to simulate it and so on. So it's that little cognitive package deal that most interests me here, that you've got an account of perception which is rich enough to give you understanding and imagination and perhaps something quite close to simulation-based reasoning all at the same time. It also has an inbuilt account of action, but I'm not even going to try and get there in 5 or 10 minutes. Okay. So perception as prediction, the kind of classic papers here are maybe Round Ballard, 1999, Predictive Coding in the Visual Cortex, Liam Mumford, 2003, Hierarchical Bayesian Inference in the Visual Cortex, and then a whole flurry of work by Carl Friston and colleagues at University College London since then, starting with the 2005 paper, A Theory of Cortical Responses. So I think they're the kind of classic read-ins in this sort of area. Just to give you that, this is a slide that I used in my introduction of Dan's use of the Basian stuff. Just to give you a sense of how this helps resolve sensory ambiguity, for example, just read those lines across the ABC or the 12, 13, 14. That's exactly what it looks like to you. But the bit in the middle, of course, as a sensory barrage hitting your eye, is exactly the same. So something explains this difference. In hierarchical predictive coding world, what explains the difference is the top-down hypothesis, which is being primed to win, if you like, by the preceding flurry of sensory processing. So when you read the A, your B hypothesis gets primed to win, and that's why it looks like a B. when you read the 12, your 13 hypothesis gets primed to win, and that's why it looks like a 13. So in the context of reading the 12, the 13 hypothesis makes the very same barrage of raw visual data most probable. And that's what the story looks like, except you have to think of this as a multi-level story, not just a simple couple of layers as I've got there. So the question that is normally asked at about this point, when I've just barely got the idea on the table, is, well, but you need to know an awful lot about the world already in order to deploy all this knowledge, multi-layer knowledge about what might be out there, in order to do the predicting. So where does all of that knowledge come from? I think the important thing here, and this is the link back into a lot of old connectionist work, is that the prediction task is just a kind of bootstrap heaven. You know, if you want to predict the next word in a sentence, it's really useful to know a lot of stuff about grammar. But if you want to learn a lot of stuff about grammar, one way to do so is to try very hard to predict the next word in a sentence and to correct your early mistakes using simple gradient descent learning schemes that are actually fairly well understood. So the big advantage then is the world provides the training signal needed to slowly correct your first bad guesses. So this is either, some people call it unsupervised, some people call it self-supervised. I don't care which of those you call it. But it's learning that doesn't require an explicit teacher. The world does the job. So suppose you guess that the most likely sound after hearing me say the cat sat on the is sofa. Well, if you were thinking sofa to yourself, the world's going to come along mostly and correct you. Most times when you hear the cat sat on the next thing you're going to hear is mat. Okay. So you can use that to progressively improve your guessing. And in effect, that's all that the kind of gradient descent learning algorithms ever had to do. So you use the prediction task to bootstrap yourself to the knowledge that you're then going to use in the prediction task in future. And that turns out to be a version of empirical Bayes. Basically, you infer your own priors from the data as you go along. Okay. So this is widely used. It works. You can see it working in a lot of sort of top-class machine learning stuff. There's a nice review paper by Geoffrey Hinton, Learning Multiple Layers of Representation. Same broad kind of story. There's lots of sort of subtle differences between the various algorithms that various people use. Hinton stuff isn't, strictly speaking, predictive coding, but it's got all of the same kind of basic elements. I'll point out where it differs in a second. But at this point, I've got a rather blank slide here because this is where I get to wave my hands rather a lot. This is a big hand-wavy slide. What you have to now do is imagine this on the grandest scale that you possibly can. So if you've got that kind of story, the brain is kind of active, busily buzzing, trying to predict the incoming flow of sensory information using knowledge that it's acquired by trying to predict the incoming flow of sensory information. Maybe that brings the whole of our structured world into view. To predict text, learn about words and letters and strokes, eventually meanings. To predict other plays of sensory data at many other scales of space and time. Learn about stuff like tables and chairs and cats and faces, glaciers, icebergs, goals, intentions, and so on. I think it's an interesting implication of this stuff that nothing is more hidden than anything else, really. So, you know, the knifeness of the knife and the mental states that I infer to make sense of your behavior are all on a par. And I think actually qualitative features of our experience are in there too, as we were looking at in the Dan stuff. So finally, let's just chuck in the data compression strategy known as predictive coding. So what I've given you so far is a story which you could think of as a broader story that I call predictive processing, that encompasses a lot of current empirical approaches. But predictive coding, technically, is just slightly more specific. Predictive coding says, as the brain engages in this task of trying to predict the incoming sensory data, all that needs to be passed forward are deviations from its predictions. So that's to say residual errors, the difference between what you're predicting and the incoming sensory evidence is all that needs to drive forward processing. So deviations from what you're predicting result in prediction errors, and these are used to refine the prediction until the sensory signal is accommodated. Basically, that's where hardline predictive coding differs from the way that it's used by Hinton and people like that. They are willing to combine the incoming stuff with their expectations in any way at all to get a particular job done. They're kind of after technical solutions to image processing problems in the real world and so on. And it turns out to be very useful to kind of tweak your solutions in different ways for different tasks. But as a generic account of what the brain might be doing, personally I favour the strong predictive coding story because it's attempting to offer a more unified account. So, prediction error for the predictive coding hardliners carries the news, is a sort of anti-hero of this whole family of models. It now performs the task that you used to think sensory information performed. So what flows forward through the system and predictive coding world is prediction error, which is deviations from your prediction. So I'd say actually that is sensory information. It's, as it were, it's the elements of the sensory information that are as yet unexplained, and that's still sensory information. And in mammalian brains, this is back to those same readings, this is all supposed to occur within a hierarchical multi-level cascade of cortical processing. So I'll say a quick word about a couple of implications, give you a demo and then stop. I can do this in 5 minutes, I think. So, implications. Some things I believe about this. I think this is why we perceive a structured external world and not sense data. You know, what's going on here is you have to meet that incoming barrage of sensory information with this complicated top-down knowledge-driven cascade that is identifying hidden causes in the world at many different levels or layers of space and time. So, you know, as I saccade around the scene, I get sort of subtle differences in texture gradients. They're quite fast changes that are part of my model that I use to predict the incoming data. But there's stuff that changes more slowly too, like your identity. So, you know, as I move around, your identity doesn't change. That's a slower changing thing that is still, I think, actually forming part of my qualitative experience. So I'm a kind of rich qualitative experience person. I think that's the most natural view to have on this story. So I think the transparency of perceptual experience is a kind of freebie with this story, that we seem to see tables, chairs and bananas rather than sense data. Perceiving and understanding come out here as co-constructed, and our percepts are always at least weakly conceptualized. So you can see here that, you know, if you get to grips with the incoming sensory signal by having the kind of knowledge that allows you to predict how that signal changes at multiple scales of space and time, I think that just is understanding. That's what it is to have a grip on the world around you and how it's going to change. Clearly, an upshot of all this stuff is that top-down effects are pervasive. They will thoroughly permeate our perception of the world. What we see, taste and feel will be highly impacted by what we expect, and there'll be all sorts of seepage between information coming in through all the modalities insofar as it can help predict what's coming in through other modalities. So McGurk effects, all that sort of stuff will come out for free. And lastly, perceivers like this are imaginers too. So basically, in order to do the prediction task, you have to have the resources to generate at least an approximation to the incoming sensory signal from the top down. That means that you're in a position to imagine your world when you're not actually actively engaging it. And I think that means that these accounts are quite closely poised towards giving an account of sort of higher level kinds of reasoning and understanding. So, summary of the proposal, demo and stop. Summary is, hierarchical, multi-level, probabilistic models are acquired through prediction-driven learning and applied top-down to predict the sensory signal. I think this is very much like the slogan coined by Ramesh Jain many years ago, perception is controlled hallucination. That's the way to think about this.
Who said that?
Ramesh Jain, the neuroscientist, vision neuroscientist. I think it's Ramesh Jain that said it first, but I've never been quite sure, because I've also heard it from Max Clouse, a machine learning guy, and Rick Rush uses it and attributes it to Ramesh Jain. So if anyone actually knows who said it first, that would be kind of handy. So you could say your brain is trying to guess what's out there, and to the extent that that guess matches the incoming sensory data, we perceive and understand the world. The same process can mislead you. So some of you will have seen the hollow mask or hollow face illusion. Hollow mask, I think, is the right word for it. Hollow mask illusion. This is a Charlie Chaplin mask. That's the same mask viewed from behind, but actually it will look to you, even in the real world, if you're viewing that mask, as if the nose is sticking out. That's the sort of stuff that Richard Gregory used to use in these demos. And the idea there is that, you know, you have a very strong prediction that sort of gives you faces as a big sort of item in your encountered world. Faces have noses that stick outwards, and so your strong prediction of the nose sticking outward now overcomes the other elements of the incoming sensory signal. You decide on the basis of your prediction machinery to treat the other elements, the ones specifying that it's actually an inward-facing mask, as noise, and you just ignore them. And there's lots of nice demos of this sort of thing. There's, you can move it in the other direction. Some of you will have seen the stuff where there's students were played a tape and they were told that it would be a noisy version of White Christmas, a famous Bing Crosby song. They were told that the song would start up at an unexpected point somewhere through. It would be quite hard to hear where it starts. And I think a large number of the students, undergraduate students, and actually after that they did it on everyone, were able to, thought they detected the song. But there was no song there. It was just white noise. It wasn't White Christmas. And we all know that we can do this. We can see faces in the clouds. We can pick up structure by strongly anticipating that that structure will be there. Interestingly, that effect is diminished in schizophrenia and under the influence of certain drugs, the hollow mask illusion. So there's a whole dimension of this that, again, moves towards exploring qualitative experience by trying to understand unusual cases. So last thing I'm going to do is just play you a couple of, if I can, a couple of sine wave speech demos that I think give us a sort of feel for the huge difference that a little bit of prediction can make. If they're going to work, I don't know. Let's see. What I want is these ones. Ooh, I can't really see what I'm doing here. Yeah, there's one. Sine one. No. That didn't come through the main system, did it? Let me try the other hole. Is that coming through the main system? Anyway, you can hear it, but I've played you the wrong one here. Sorry about that. I played you the answer to the question that I haven't set you the puzzle of yet. Right, okay. So this is what I want, I think. No, I'm getting the wrong one. Okay, something bad is happening here. Let me try something else. We'll give up on this if it doesn't. Yeah, we're going to give. For some reason, I think I've got all the originals and none of the sine wave speech. I was trying to put this together in a little bit of a hurry there. There's here's one that I know I can do. So let me just try this one. There. So that's what they all should have sounded like. You probably can't hear too much there yet. Let me play it one more time. Maybe. Gosh, I hate it. So now you may get there. Once upon a time there were 3 bears, mummy bear, baby bear, little bear. Try again. And they lived in a big house in the woods. No. No? I can hear it so well. But my priors are better than yours.
That's because your priors.
That's what I'm saying. Let's see if I can get one more. It would be really good to get one of the simple ones. So that was, you were supposed to be trained on all the simple ones first. There's one. Try that.
Kettle boils quickly.
Exactly. The kettle boils quickly. One more time now, you all know what it is. Maybe. There, we got one. So they're all like that, if I can make the work properly. But anyway, so once your prediction machinery is tuned to the incoming sensory signal, then of course the signal sound is just transformed. You see through to the meaning as well. So there we go. That's the end of my my quick comments.
Angelina has a question, I see.
Thank you, it was very interesting. I just wanted to ask you, if perceptions are predictions, how our first perception happens? I think this is a question that bothers me in this theory, but in general I think it's definitely right.
I think that's a great question because it also gives us a chance to think about perception in two different ways, if you like. So in one way, perception is being able to encounter sensory data from the world. And you have to be able to do that before you can get these stories going. What you don't have to be able to do is have a good hypothesis about, as it were, what's shaping that sensory data, what's making it the way that it is. So the idea is that the young system, I mean, maybe we're kind of born, probably we are born with bunches of knowledge in place that allow us to make some sense of the incoming sensory data already. But even supposing you weren't, there are demos here in the machine learning world where you start your system off with no knowledge at all. It starts with a structure, so we could talk about that. But it starts with random weights. It's hit with incoming energies from the world. And over time, by slowly by doing the basic connectionist trick of gradient descent learning, slowly changing its weights to better predict the incoming signal, it ends up having knowledge about the hidden structure in the world, learning stuff about different letters or digit forms or the grammar of sentences or parts of images. So the idea is that early experience might be a complete sort of buzzing confusion that only slowly comes into focus as the prediction machinery takes shape. Or maybe it's not quite just a confusion because, we've got some innate knowledge already of what's likely to be shaping the sensory signal. So I think one other benefit of this story is it's quite neutral on the question of whether there has to be an awful lot of whether there is a lot of innate knowledge or whether there isn't. It seems to give you a way of making progress without actually solving that problem at the outset. So I don't know if I managed to make sense of that properly there or not to give you the reply, but the idea is that think of perception in the case where you've not got a good predictive story in place as just being exposed to lots and lots of sensory stuff, and that you're then going to try to find ways of predicting that stuff, and that means finding patterns in the incoming sensory stimulations. And those patterns, if this story is right, our whole encountered world just is those patterns. The world of people and identities and textures and qualia for that matter. It's just stuff that we infer in order to get to grips with the patterns in the incoming flows of sensory data.
Are there other questions over here? Somebody out here?